Here we're going to continue with part 2 of the video about domain and range of functions, and we're specifically going to talk about piecewise functions. Now, back to the definition of a function, we saw that a function consists of 3 parts: a domain, a range, and then the rule that assigns between each input value a unique output value. But it happens to be that the rule that's used to relate the input and outputs can be expressed with more than one formula, as long as we have the criteria that still each input pairs exactly with one output. So if we have a function that is defined by more than one formula over specific pieces of the domain, that is what's called a piecewise function. And the visual identification that you're looking at a piecewise function is you'll have the function described with some kind of output variable followed by parentheses the input variable. This will change based on what problem you're looking at. But then it's followed by a large bracket where you've got a list. It says if your domain follows some rule, then act like formula 1. But whenever your domain is now like domain 2, act like formula 2. When your domain is now in domain 3, act like formula 3. And probably the piecewise function that we're most familiar with is the absolute value function. It can be written like this as a piecewise function. The absolute value function acts like the function x whenever the domain is positive or equal to 0. And it acts like the function negative x for all domain values that are less than 0. Now, positive x, our first formula, is just the straight line through the origin with slope 1. So that's saying if you're equal to 0, we know the absolute value of 0 is just 0. And then if you're all values greater than 1, for instance, if you input 1 into absolute values, since it's already positive, you just get 1 back as a result, which is why the function can be described for all positive values as just the line y equals x, because the line y equals x for every input, you get exactly that out as an output. So that covers the first part of the domain. But the second part of the domain is all negative values. So for all negative values of x, for instance, if we look at the absolute value of negative 1, it just gives you the positive version back as a result, so you get positive 1. So if you go over to negative 1 in the x, you get back positive 1 as a y. Similarly, negative 2.5, you just get positive 2.5 back. So if we go over to negative 2.5, we would get positive 2.5 back as a result. Continuing this on for all x values less than 0, and we see we get the line y equals negative x for this portion of the graph. So it's not that one equation defines the function over its whole domain, because for the first portion of the domain, for all values when x is less than 0, we had the function y equals negative x. But for all values equal to or greater than 0, it then acts like the different function y equals x. So this is our first introduction to a piecewise equation. Let's look at our next examples for graphing piecewise equations. So the structure will be, we're going to graph this next piecewise function together, and then what follows up is another graphing of a piecewise function that I would recommend at that point you'd pause the video, attempt it on your own, and then unpause. So let's do this one together so that you can practice the next one on your own. We're asked to graph the following function, and it says functions because there's another example after this, but we're just looking at the function f of x here. We notice it's a piecewise function because we see these brackets, and then they describe the domain for search and restrictions. So if we're reading this, we've got when x is less than 2, the function acts like x squared. But when x is greater than 2, the function acts like x. And looking at this piecewise function, do you see that the key point of interest is about 2? All the behavior switches about 2. So I know that's going to be an important point on my graph. I recommend when you're graphing a piecewise equation, one approach could be that you make a table of some relevant values. So 2 is definitely going to be part of it because that's kind of where the function changes over. If you can imagine a relay, whenever they pass the baton, that's kind of what's happening here. The function acts like x squared all the way up to 2, and then at 2 it changes hands, and then it starts acting like the function x for all values greater than 2. Now we've got our key point 2, but let's also include some values before and after. So I just picked nice values to work with before and after 2, and let's evaluate these in the function. So the way you would work through a piecewise function, if we were looking at f of 0, so this is saying what's the value of the function when the input is 0 to get this table value? Well, we'd have to ask ourselves, are you in the part of the domain where x is less than or equal to 2, or are you when x is greater than or equal to 2? Well, since our x value is 0, 0 is less than 2, so we're in this part of the function. That means at this point the function acts like x squared. So for the input 0, the output says just square that value, and we would get 0. Now for practice, why don't you find the output value when the function takes on the value 3? So here we've got that 3 is definitely greater than 2. So now we're in this part of the function, which means it acts like the function x. So whenever we've got the function x, that means whatever input you give it, it gives that immediately back as the result, because that's how the function y equals x works. Take a moment to fill in the remaining pieces of the table. I recommend you would pause the video now, fill in the corresponding y values for 1, 2, and 4 as x values. Unpause to check your work. Okay. Now when x is 1, we are still less than 2, so we're acting like the function x squared. 1 squared is 1. Now since the inequality said less than or equal to 2, at x equals 2, we still act like the function x squared. So we've got a square 2, which would give us 4. Now when we are at 4, 4 is strictly greater than 2, so now we're acting like the function y equals x. Inputting 4 into the function y equals x, we would get 4 back as a result. Now let's start to graph this on our coordinate axis. So graphing these xy coordinates, we would get this. And at this point, we need to think about how the separate functions look. For instance, for all values of x less than 2, the function looks like x squared. Well, in general, I know x squared looks like this. Now, the graph is not going to always look like this because at 2, it changes direction. So at 2, it starts acting different. Let's see how it starts acting different. After 2, it starts acting like the function y equals x, which we know looks like this, but it doesn't act like this always. About 2 is when it changes direction, so it only acts like this after 2. So piecing these together, we can kind of get the idea of what the function looks like. We know for all values greater than 2, or sorry, less than 2, it looks like the parabola y equals x squared. But at 2, it changes behavior. So it ends up here at the parabola, but then for all values strictly greater than 2, it now starts acting like a straight line. That's why we've got this kind of behavior. But if we just leave it like here, we've actually graphed the wrong thing, because if we don't do anything further, do you see that there's no x values graphed between 2 and 3? Which is inaccurate, because immediately after we pass the value 2, we should be acting like the function y equals x. So that means we actually need to continue this graph down, but we cannot let it equal 2 because it's strictly greater than 2. To show that it's strictly greater, we do this open circle here to show that it's approaching 2 through this pattern but not equaling, but everything greater than 2, it acts like the function y equals x. So this is a graph of f of x. Now, our next example asks you to graph this different piecewise function. And I would recommend that you take some time to pause the video now and work through graphing this. I'd first read through it to yourself, understand the different pieces of the function on what domains, then make a nice table of carefully chosen x, f of x values, or x and y values, another way to say it, and then graphing it all together here. Whenever you've finished all that, unpause the video and you'll get a step-by-step explanation so you can check your work. Now first, when looking at a piecewise function, it can be helpful just to read through it. Notice for all values less than -1, the function acts like absolute value of x. For all values between -1 and 0, it acts like x squared. And then for all values greater than or equal to 0, it acts like the function x. And I would say of all these three, this is the one that we know the most about. So specifically, when x is 0, because it could be or equal to 0, right? We're exactly at 0, 0, because that's how the function y equals x behaves. And then for all values greater than 0 means for this entire positive x-axis, we are acting like the function y equals x. But we know exactly what that looks like. We know it looks like the straight line through the origin of slope 1. So if you want, this could be kind of a shortcut for pieces of the piecewise function that you understand well along with their domains. We can just graph that. And if we were going to make a table of values, the key points seem to be about -1 is when the changeover happens. And then it changes over again at 0, or about 0. So as we make a table of values, we'll want to make sure that we include those key points and then values also before and after them. So let's write down we need -1, something before it, something after it. We need 0, something before it, something after it. So before -1, maybe I'm going to pick -2. Since I can pick any value, I might as well pick a nice value. Between -1 and 0 is -1/2. And after 0 could be maybe +1. Now we already know what's happening for values 0 and greater. It's acting like the function y equals x. So at 0, it's 0. At 1, it's 1. Now for values that are before -1, it's acting like the function absolute value. So if we put in -2, that's definitely before -1 into the absolute value. We would get 2 back as a result. And specifically, it's like this until you're equal to -1. So we would also say for the x value -1, the function f of -1 looks like just the absolute value, added x, f of x of -2, which gives us +1 back. But things are different whenever we're strictly between -1 and 0. That's when it acts like x squared. So f of -1/2 is acting like -1/2 squared, which would give us +1/4. So we would next maybe plot some of these points in if needed. You could also add in more x values, so more values between -1 and 0, just based on what is useful to you. And you could write in more like that. So for instance, -3/4 when squared would be +9/16. But not necessary, just helpful. If it is helpful, feel free to graph more points. And we know the function absolute value of x for negative values is just the line through the origin of slope -1. And since x is less than -1 is definitely through all negative values, we know for everything smaller than -1, it's just this straight line of slope -1. The only thing we've got to figure out is this remaining piece, what's happening between -1 and 0. And we've got to make sure that we graph that, what's happening on this domain, right? Because we need the function to act like x squared from -1 to 0. Now, I know the function x squared is one of my well-known parabolas. It looks like this. And this is how it looks over its whole domain, but we are restricting it to -1 and 0. So we can just think of like we are forgetting this portion and forgetting this portion, right? And what are we tacking on to that is the straight line -x and then the straight line 0. So we could connect this by, if you like to graph the -1/2, goes down to 1/4. But it's just a little piece of the parabola here. That's what we'd be looking for. So that would be the graph here where it's the line -x until we get to -1, and then it's the piece of the parabola x squared, and then it's the straight line y equals x again. So that finishes up the notes for 1.2.